Are we going to review? All right, so we've been talking about AC circuits. There's your review.
Thank you.
All right. And for a more detailed review, read your notes. All right, we're talking about AC circuits, and we talked a lot about phase yesterday. What else we talk about? Oh, why it's AC, how it comes about. Looked at a generator. And now we're moving on to AC resistive circuits. When we talk about AC circuits, I can back up. When we talk about DC circuits, we just look at everything as resistance. It just has resistance. But when you get into AC circuits, it becomes much different. We have RCL, so we can have resistive, capacitive, and inductive circuits. So we're going to talk about resistive, then inductive, then capacitance. So RLC is the order we'll do it in. So when we talk about an AC resistive circuit, is a circuit that contains only resistors. It is a circuit that contains only resistors. And that brings it right back to what you've already learned. So Ohm's law is applicable just like with DC. Off the top of my head, I can't think of anything that changes. If you have a series circuit and you have a bunch of resistors, the resistance is what? What's the formula?
The sum of resistors. Total resistance.
Well, at least one guy knows. You guys remember Ohm's law, right?
No,
Yes. And resistors in series, you add them up. And if it's in parallel, that's a blah, blah, blah. So, I know. The total resistance is smaller than... Oh, our lights are coming back on. All right. And if you're going to measure current, you would measure it in series. Wow. All right. All right. I have an example here, but I'm not going to waste time on the example because if you don't know it by now, you don't know it by now.
So it's exactly the same.
Exactly the same. So here, just to keep everything, example. You should know this. D. So I should be able to make any example I want. I had one in here where it was 110 volts RMS AC power supplying two parallel resistors of 10 ohms each. What's total resistance? What's total resistance of two 10 ohm resistors in parallel? 5 ohms. All right. So you should be able to figure out everything from there. So anyway. We're just moving on from there. Okay. D. In a purely resistive. What does that mean? Resistive circuit. What does that mean?
The resistors of the loads.
That means that's all it has. All it has is resistors. Are there any capacitors?
No.
Are there any inductors? No. So it's purely resistive. That's all you have. So in a purely resistive circuit, volts and amps are in phase. Which means that, just like the drawing I had yesterday, when volts is at 0, amps is at 0. When volts reaches its peaks, amps reaches the peak. When it comes back to 0, amps are at 0. So it's lockstep in every which way, going to follow it. It's just not the same amplitude because amps aren't as tall as volts. Everybody remember that from yesterday? Okay, so in a resistive circuit, is it in phase? Yes. All right. I don't know, maybe I could. I wrote, you want me to write this one? When voltage reverses, amps also reverse. In every step in time, volts are doing the same thing as amps, but at a different amplitude. So, the power consumed. The power consumed by this type of circuit, is the same as DC. Oh, anybody remember that one? P equals I times E. But we could look at it this way. Power equals I RMS equals E RMS. All right, then I have a simple equation, which we don't need to do, because you got that. And honestly, that's about all you need to know about a purely resistive circuit. It's just Ohm's law as you already know it, hopefully. Nothing changes. Volts and amps are in phase. See where I'm going with that? I'm moving right on. Wait, you're saying that volts and amps are in phase? Okay, yes. All right, but now we're going to move on from that. But before we can move on to that too far, we got to talk about some things here. Magnetic fields. All right, inside of a wire, talk about a wire. Magnetic fields in a wire. All right, trying to decide if I want to use my notes or not. What the heck? In a current with no voltage, in a circuit with no voltage, free electrons randomly move around. So we talked about a wire back on 309, even day one, pretty much here. And a wire, we'll say it's made out of copper, and you have your copper atoms in there, and then you have your electrons, and they're not just sitting there, right? They kind of move and bounce around a little bit, but they don't really do anything because it's more of a random pattern. So we don't really have current flow, right? Okay, so because of this randomness, a piece of wire has absolutely no magnetism. But when current starts to flow through the wire, now you have electrons are all moving, and they're moving pretty much the same direction. So when they're moving in the same direction, their combined effort actually does create a magnetic field. So you have this magnetic field. The magnetic force extends outside the conductor, and as voltage is increased, current is increased, and the magnetic force is increased. The force of it's considered, use a left-hand rule of thumb. So if you wrap your hand around a conductor, your thumb points in the direction of current flow, and your fingers show the direction of the magnetic field, which, again, I'm not going to make you remember these rules because it doesn't matter if I say that this is my conductor and current's flowing this way. I have a field that's actually going this way. Or if I said it's going this way, you have a field that goes around a wire, this electric field. Yeah.
Is that what creates like radio interference? Like the
Yeah, to a point, but it's higher voltage, but yeah. And it gets stray. So let me write some of that stuff. Let me try and consolidate it. But you do have a magnetic field in the wire. So where can we go with this, just to make it quick? How about this? When current flows through a wire, a magnetic field is created. A magnetic field is created. Let me see. The magnetic force extends. The magnetic force extends beyond the wire. So you have this field that's actually bigger than the wire, right? It grows out. And this magnetic theory that we're going to build upon, it's another thing that we're going to build upon again as we get into magnetos especially. We're going to do a lot of magnetic stuff with me for the next 8 weeks, basically. Yeah, from here on out, the next 8 weeks that I teach. So it's this last 4, and the 4 when I come back, we're going to talk a lot about magnets. All right, magnetic field extends beyond the wire. What else can we put here? We could put here, it's the left-hand rule. Left-hand rule. Just because I mentioned it. All right. So what is the thing? So what? Okay. So you remember we have in a generator, we have this magnetic field, right? Sorry, go back to a generator. How did we create electricity? Okay, so we have a magnet and we have wire. All right. So one part of it is a magnet. Well, what happens to a wire when I run current through it?
Creates magnetic field.
It becomes a magnet. Okay, so we got to keep this in mind. So a magnet and a piece of wire with relative movement creates electricity. What if I hold the wire still and move the magnet?
The same.
Still.
Okay, what if I hold the wire still and the magnet still, but I change the field back and forth? So the magnet's actually not moving, but the field it generates across the wire is growing and collapsing, growing and collapsing, growing and collapsing.
Yep. I think it-
So I still have a wire and I still have
magnetic field.
relative
Not too
movement.
much.
Okay, so everybody follow that? So I come up with 3 ways that I can sort of create electricity here, knowing I need a magnet and a wire. So one, I can get a permanent magnet or electromagnet, which is just a magnet that you plug into the wall, or a battery. Battery would be a better example. So I can move the wire through the magnetic field. Okay, or I can hold the wire still and move the magnet. Just like that little toy that I showed you guys yesterday.
Yes.
Okay, the wire stayed still, the magnet moved. Or I can hold the wire still and the magnet still, but take the field that the magnet is creating and use electricity, make it grow and shrink, grow and shrink, grow and shrink. Got it? So if I can change that magnetism that's growing and shrinking, I can also create electricity. So now let's stop and think about a wire that's plugged into AC. Voltage builds, voltage collapses, goes the other way. Then it builds, goes the other way. So you have a wire that has electricity flowing through it. What's happening in that magnetic field?
Expanding and contracting.
Expands, contracts, expands, contracts. Not only does it expand and contract, but if we go back to the left-hand rule where I say the direction of flow of current, your fingers tell you which direction the magnetic lines of flux are actually rolling. If I have it going positive, we can say the magnetic lines are going this way. Then it's going to reverse. Magnetic lines actually reverse the other way. And so that's going to have a bearing on what we're going to talk about. So you have to remember that the actual lines of flux are even going to reverse upon themselves. Yeah.
So when you said you send electricity through the magnet for it to expand and contract,
Uh-huh.
so are you sending the same amount of electricity through it to expand and contract as it's producing? Does that kind of make sense?
No, that did not make sense.
When you send the electricity through the magnet
Yes?
to make the force expand,
Yes?
wouldn't that be using the same amount, if not more, than the electricity?
Amount of what?
Amount that it takes electricity. to
Let's just,
expand.
let's, no, it doesn't. Otherwise we'd have perpetual,
Yeah.
we would have created a perpetual machine there, and it
I
doesn't
think
work
he's
that way.
asking like if you convert the, I guess, power,
Yeah.
electricity, into the power magnetism, is it the same?
No, it's not. You always have losses.
Okay.
Yeah.
So the only reason that AC works is because of how fast the phases are?
No.
No?
So, no, it would work even slower, but
Oh.
not efficiently. So, all right, but I wanted to kind of talk to you about this magnetism. Now I'll write some stuff. So what we end up with something called induced EMF. And that is going to be a problem with electricity, with AC. What's EMF stand for?
Electromagnetic field.
Electron moving force, or electromotive force, or but it's an electric force. It's kind of like electric resistance, if you will. So it's not a physical resistor this time, but it's more of an electric resistance. So, and I'll make some good notes here. So let me think. As we talked about with a generator, a wire moving through a magnetic field will produce voltage. Okay. So as we talked about, these are the things I could probably leave off here. Maybe about with a generator, a wire moving through a magnetic field, or I could say relative motion between a wire and a field. So a wire moving through a magnetic field will create or produce voltage, which is another word for EMF. All right, with DC, the voltage goes from 0 to max almost instantaneously. So with DC, voltage, the voltage goes from 0 to max pretty much instantly, as long as the current's flowing. You have a circuit. Once you blow the fuse in the Simpson meter, it stops flowing, right? As does the EMF. All right. So you have your DC circuit. All right. You just got a couple resistors in there, some LEDs, and you close the switch. Everything happens just that fast, right? Speed of light, pretty much. And if you charted it out in time, it would go from 0, and this is max. It would just go 0 instantaneously, and there it is. Right? And your circuit is just done. And it's just going to stay there if you've got resistors. It doesn't take any time to build up, and it just goes. So that's what the graph would look like. Off, max, go. So we would say that's 6 volts. This is 0. 0 to 6, boom, you're done, right? Mm-hmm. Okay. AC is not going to do that. The reason, let me see. There is actually EMF that's built up in the wire, counter EMF, so to speak. And what happens is, because there's a change, and I'll explain this more in a little bit, because there's a change, whenever you have a change, it's going to want to push back against the electrons. So in reality, but it doesn't really work with DC this way, because the wires are just, you're not dealing with enough stuff. But there's this counter EMF that's built up. Counter EMF, again, is like electric resistance. So whenever you have a change in the voltage, so we have that brief change, what's happening is you have a magnetic field starts to expand in that wire. It's building, it's 0, right? And it starts to build up. Well, that's change. So you have this counter EMF builds up in the wire. It's building up because the power is coming on, and this buildup is opposing to the current coming in. So as you turn it on, again, what's happening is the counter, the voltage and the amperage starts to go. You get amperage through the wire. The wire then has electrons moving. It's movement. It's a change. So the change builds up the magnetic field as it's expanding. It stops the electrons from coming in. I don't want you coming in. But once it's built up, it's there. And there is no counter EMF because there's no change. All right, I'll explain this more. But hopefully you can kind of get that. So let me see. When voltage reaches the max, counter EMF stops. So that's kind of what I explained, but let me see. I'll leave that one off, but I'll write this one. With AC, the voltage is constantly changing, which builds and collapses the magnetic field around the wire. This creates an EMF that counters the flow of electrons. It's pretty much what I said. I don't know how I can... Let me see. Well, I'm sure it makes sense. With AC, the voltage is constantly changing. Because it's constantly changing, where am I here? Constantly changing, which builds and collapses, which builds and collapses a magnetic field around the wire. This creates an EMF, electromotive force, that counters the flow of electrons. Follow that? Yeah.
Wait, it's basically the voltage creates an EM or magnetic field, and then that magnetic field causes the voltage in the other way.
Technically, it's the flow of electrons, so it's amperage. But so yes, the buildup of the current coming in is change, causes a magnetic field, which stops anybody else from coming in. To personify it. Now it's too bad because if it worked the other way around, if the buildup of current caused a magnetic field that pushed electrons through, I think we could build something we could turn on and just remove the battery source because the electromotive force would keep everything going. But it doesn't. It fights it. It stops it. Which is too bad.
So what do you mean it builds and collapses the magnetic field around the wire?
Okay. Let me see if I'm going to... Well, we'll make sure we understand that. So now we're talking about AC. So we have the curve that builds up. So we start with 0, and as voltage, and of course voltage we have amperage, builds up, what happens is a field starts to grow in the wire. Because it's growing and not static. Remember, we create electricity not by something being static. I just don't take a piece of wire and put it in a magnet and just go, whoa, where's my electricity? You got to have some sort of movement, right? I was going to do it like that, but that's it goes back and forth or around. So it reminds me of a joke that I won't tell you. Ask me a break. So because there's this relative movement, the field itself is growing in the wire. And all it is just one wire in its own field stops more, doesn't stop it, but it fights more electrons from coming into it. Now with wire, we don't really notice that. With AC, we don't even consider it necessarily. It's just a straight piece of wire. It's fine. We just call it resistive. Right? But, huh?
Does the electromagnetic field have to be acting on anything?
It's acting on itself.
So it's just itself.
It's just itself. It's just this piece of wire. So as the voltage starts building up, we have change. We have change. The field grows. It kind of cuts across itself, which stops electrons from flowing in. Yeah.
Is that like the same way, like saying it's just creating more resistance?
It creates more resistance. But I'm going to go somewhere with this that'll make more sense. So I hope. All right, so we take that, and let's see, I'm kind of screwing up my timeline here, which creates something. Now we talk about Lenz's law. And what that is, a change in current, produces an EMF whose direction is such that it opposes the change in current. Which is to say that a change in current, in other words, when we have the voltage going up, it's going to create a counter EMF that wants to keep the amperage from following it. It's saying, no, you can't. You can't come in. We're building up our voltage over here. You can't come this way. Well, it's going to anyway, but it's going to take a while to get through the door.
So it's like a little brother.
Yeah. Her sister. I mean, all right. I'll just go with these just because if, I said this already, if the EMF added current, just to kind of help you think about it, opposite, added current, it would cause a runaway. It would cause runaway current. And I'm simplifying that, but if you can imagine that, if a buildup of this EMF actually helped bring in electrons, well, then it would just kind of grab and pull them through and be like, whoa, hey, we got to, You get this runaway current flowing. Why? Because of the buildup of EMF. All right. When current is increasing, the EMF, this is redundant, I've already said this, the EMF opposes the increased current. The opposite is true. When current is decreasing, the EMF tries to keep the current, C-U-R-R-E, current from decreasing. And last point here. The EMF, or counter EMF, which is also called CEMF, counter EMF, is 180 degrees out of phase from applied voltage. All right, so what does that kind of mean in simple terms? Heck if I know. All right, so we're just talking about a piece of wire. And we're talking about, we talk about DC, we have this instantaneous buildup. So during this buildup of and then it builds up, and then what does the magnetic field do in DC? Just stays there, stays the same. So we have this initial, something we haven't talked about, we turn on a DC circuit, we have this initial buildup, and during that just very brief moment of time, you have a magnetic field that's growing across or around the wire, and that tends to want to slow down the amps from flowing, but it's so fast that we don't discuss it in DC terms. But now, because we have AC, which is constantly turning on, peaking, going to zero, going the other way, turning on, peaking, going the other way, and it's constantly stopping and reversing, we have to think about it. So what happens in wire, or more importantly, where we're going this, an inductor, and what is an inductor?
Coil.
It's a coil of wire. Okay, so we take wires, now coil it up, and this compounds the problem. So what happens as the voltage is ramping up, it's building this magnetic field that says to the current coming in, stop, I don't want you coming in here. Now some of it's going to get through, but it's going to delay it. That gets it out of phase. Now it gets worse. So finally, we get to the peak, we build up, and the change doesn't happen so fast, because believe it or not, this is something kind of you have to think about, is if you look at a sine wave, you have to think about a couple of things. One, the greatest change doesn't happen from here to here. It happens from here, and I'll make the dot the same. It happens from here to here. So between here and here is the greatest change. There's very little change between here and here, these two spots. There's a lot of change between there. Do you see that? Mm-hmm. Okay, so remember that when we talk about change in stuff. Sometimes it's the change happening that creates the most work. So we have this wire then, as the voltage builds up, it says, whoa, stop, I don't want the electrons coming in, everybody stop. And so what happens is it starts to push back on the flow of current. Okay, then it peaks out, and then, current, we don't have that problem. But then the voltage is going to turn around, it's going to go the other way, and it's going to say, stop, no, you can't collapse. So not only does it want to stop it from building up, then it wants to stop it from collapsing. So it tries to stop it from coming in, and it tries to stop it from going back out. Not that there's an in and out per se. So that means that it's going to delay the what? Current. So we can remember this by Eli, which means that what leads what? Now you know why amperage lags behind. What number am I on? 5. I care. Oh, we left out one thing. Probably should have. 5. Okay, the amount of self-induced EMF, which is to say EMF is not all the same. It could be worse or it could be not so bad. So the amount of self-induced EMF is dependent and proportional to 3 things. And Tim is going to tell us what those 3 things are. Tim, go. What? What was not one of them, but good try. Frequency. More changes equals more EMF. So the higher the frequency, the more counter EMF you're going to get. So if we have a circuit and you just increase the frequency, it's going to have a tremendous effect on it. 2, current flow. More current equals more EMF. More current would equal more magnetism. More magnetism, more EMF. And 3, physical shape. Of the conductor. Let me see. I wrote in a straight conductor, counter EMF is determined by the lines of flux. Okay, so in a straight conductor, CEMF is determined by purely by the lines of flux created. CEMF is determined by lines of flux. What are lines of flux again?
It's
It's the what? The magnetic field, the invisible magnetic fields off of a magnet. All right, so not such a big deal with just a piece of wire, but take that wire and put it in a coil, now you got a big deal. If the conductor is coiled, then the EMF from one wire, let me see, let's kind of put it here. I don't know if I can draw this. I'll try. So the EMF from this wire that's right here at this spot builds up and cuts across other wires. This one's building up and cutting across those wires. So the effect of one wire is not just on itself, but it's on all of its neighbors. Yeah, you look at that. Just look at that drawing. It explains it all right there. That's beautiful. I could have just drawn that. You'd be like, oh. Oh, I should take a drawing class. All right.
So create more magnetic, bigger magnetic field
What's that?
on the coil. You have
Yeah.
more a bigger magnetic field.
It does. Well, not a bigger magnetic field per se, but it affects the wires next to it. So in a straight run, you only have a section of wire that only affects itself. Coil it, and that piece of wire affects its neighbors.
Does this happen just once, or does this happen continuously?
Continuously, nonstop, every reversal. Where was I here? Oh, the EMF, let me see. If the conductor is coiled, EMF produced, cuts through other wires. This has an exponential, that increases the EMF, so this significantly increases. CEMF.
So what if you have a bundle of wires together? Would that cause the EMF on each other?
Yeah.
Like you have a bunch of straight line wires.
Okay.
And they're all bundled together in a bundle.
Now, straight wire. Not that I know of, I should say. Is almost negligible. Coiled wire is not negligible. All right, so what is coiled wire called? Coiled wire is an inductor. Yeah.
Can I go back to a point above real quick?
Only if you're not going to ask me why they didn't do something.
No, it isn't. A little bit hard. I think it's number one. Frequency. So, is there any time that if you go to have a frequency, does it lead the ramp up period? It can ever be faster than the ramp up, like so it'll be less efficient.
Yeah, is there? I know what
So
you're
if the
saying.
hertz rate is like
Could you get it so high that?
it can't actually build up to full before.
I would say in theory yes, but you don't want it to be out of phase to begin with, so you're going to do something to bring it back in
No,
phase.
but exactly. That's what I just didn't know if it was. And then second question is, for the coiled wire, isn't it additive? Like, I thought they add up into a bigger magnetic field.
It's exponential.
Is what?
In a coil,
In a coil, yeah,
you have the wire,
yeah.
and each of the magnetic field, like the EMF of each set coil.
Yeah, the tighter the coil is wound, the more winds you have, the more it's going to have an effect.
So that doesn't add to one bigger magnetic field that's the left-hand rule?
I don't understand the question, but I think you know the answer.
Is it additive or
Is what additive?
The force of the field in a coiled wire, is it additive or is it exponential?
Well, I don't know what I was asking.
I think we should just continue.
Okay.
Again, my apologies. Not an electrical engineer up here.
Talk to Tom.
Talk to Tom. Yeah, it really isn't such a class for designing circuits. It's inductor. All right, back on track. Inductor is defined as that inductance. Sorry, inductance. We're going to define inductance. INDUCTANCE. Inductance is defined as that property. Is that property of an electrical circuit that tends to oppose any change of current through the circuit. That tends to oppose any change of current through the circuit. So what does that mean? Well, it means what I've kind of been saying. As the voltage builds up, the inductance stops the current from flowing in. Doesn't want it to flow. It's going to, but it tries to push it back and resist it. Notice that word resist. It's like resistance. All right? And so finally, it kind of doesn't want to give up, but finally the amperage comes through and it reaches its peak. And then the voltage is already starting to fall back. And so then it turns around and goes, oh, don't go. You got to stay. It's like a bad neighbor. I don't want you to come in. But then it comes, once you're in, you're like, no, don't go. It's actually like my grandma was.
Kind of like ADT, huh?
I'll try. I can't think of how I can work that in, but that was pretty good.
Kevin,
Huh?
do you use EMF and counter EMF interchangeably, or are they two different things?
I'm using it a little bit interchangeably depending on what it's doing. So counter EMF is like that resistive stop force. So first there is EMF, there just is, and then I'm using it in a term like, well, what is it doing? It's stopping something. Well, now it's counter then.
Okay.
Now, if I just wanted to say, no, I'll just leave it at that because that kind of explains it. Let's see. Inductor B. Here we go. B. A coil of wire that may or may not be wound. So a coil of wire. I don't know. I wrote it this way. I'll just go with it. A coil of wire that may or may not be wound around a core. Be wound around a core. I'm going to talk about that. I got to move over.
That's an inductor?
That is an inductor. An inductor is a coil of wire. Inductance. Need me to go back?
No.
What?
Everyone's just looking at me. Every
Poor guy. You're like the pace car.
I know. It's okay.
All right. So subpoints under there. A core may be magnetic material, which increases inductance and magnetizes the core. So core may be magnetic material. Magnetic material, which increases inductance. Remember, the word inductance is like the resistance for a coil. And magnetizes the core. And magnetizes the core. The core may be non-magnetic. Air or insulator, which decreases inductance. Which is to say, we have a coil of wire, and we've already discussed how the magnetic field from the wire influences its neighbor. Well, now stick a piece of iron in there, and you magnetize the iron, and the iron just transfers the magnetic lines of flux all over the place, which really causes an increase in inductance. Let me see. How much CEMF, or inductance in our case, inductance is produced is determined by a couple of things. I already told you some of them. What is it?
Frequency.
How about core material?
Every day.
Core size.
Number of one.
Thank you. Right on time. Number of turns, which is the same thing as wines. Size of wire. And it is determined by the formula. No, it's not determined by the formula. I could tell you the formula, but you don't need to know it. I'll just write it. It's not something you need to write down or memorize. I just will say it because I started it. 0.4 pi times number of turns squared is microamps, all divided by the Henrys. So,
Did you just make that
the length of the core, I mean, sorry. What's that?
You
Did I just make that up?
You just made that up.
No, I didn't. I actually have it crossed out on my notes. I'm like, you don't need to know it. So that's the formula. It's number of turns. N is number of turns. Mu is the. Just chill out over there. Mu is the core permeability. See, it gets pretty. Like, let's not go there. All right.
Does that need to go on the formula page?
No, I said that multiple times. So, all right. But D, inductance. This is important. Inductance. Inductance is measured in, who knows this one? Nope. In henries. Why not, right? You're not even going to write it until you know if I'm done joking, huh?
I know.
I'm not joking.
Concerned. It sounds like a hole-in-the-wall bar.
Or a rifle.
Let's go to Henry's.
Named after Joseph Henry, partner to Michael Faraday, who gets the honor of capacitance. It's measured in farads. Henry is defined as, I need to move this here. I'm not going to write down that it was named after Joseph Henry, but so we're just going to skip right and Michael Faraday. We're going to skip right down here to Henry is defined. H-E-N-R. Henry is defined as a conductor. A conductor has an inductance of 1 Henry if a current change, or if a current that changes at a rate, I gotta move it, sorry, of 1 amp per second produces a CEMF of 1 volt. How about that? Henry's can be calculated by the formula CEMF equals, you don't want to know that, change in I over change in T multiplied by L. And I actually went so far as to create an example to prove to you that I'm right.
We believe you.
Okay.
Brent is the only one that doesn't.
But he can ask Tom. Yes?
What size of length or what or size or what?
Diameter. Thickness. All right. That sounds like a great place to stop.